Okay, this is lecture 17 for continuing discussion on the continuity equation. So let me just go to so before starting today's talk, I have one announcement. So here we have a lecture 18 on this Wednesday, and as usual, and lecture 19. So next Monday we will have just online lecture. So recorded video will be distributed. So we don't have offline lecture as usual. So next Monday, so please, next Monday we don't have the on-site lecture. Please note this one. So in this recorded video, I will give some comments on your term project proposal. So you have already submitted your term project themes. So I will cover them. Okay, that is one announcement before starting our main discussion. Okay, if you have any question, then please interrupt me anytime. Then let me just go to the discussion on the continuity equation. So previously we have thought about how can we consider this current density. So maybe you remember that we start from this vector-wise quantity Q, U, N. So this is drift term, and here we had diffusion term. That was the 3D version. However, we prefer to, in this course, we prefer to have just a one-dimensional version that is given by ES. So Q mu n d phi over dx plus Q dn over dx. Of course, by applying the Einstein relation, we can write it down in this way: dn over dt, and the remaining thing is just discretization of this dn over dx term, and the other one is 1 over bt and d phi over dx term shown here. So as you know, everything seems to be quite straightforward, and now we will just introduce linear approximation for these first derivative terms. So we just calculate delta value of electron density with in between two neighboring nodes and delta x. And also in this case we will just use delta phi over delta x. Of course, here delta x can be interpreted as xi plus 1 minus xi if we consider one-dimensional case. Also here delta n can be regarded as the difference between two node value evaluated at x sub I plus 1 and x sub I. Okay, so that was the thing we have studied up to now. So from the previous expression, we can immediately obtain this current density expression. So you can understand this delta n divided by delta x corresponding to your drift term, and here you have your diffusion term, and this is corresponding to your drift term. So d phi over dx, and I told you that the most significant part in this approximation is this one. Although we don't have any information about the electron density defined at the midpoint, we just gave it by taking the arithmetic average between these two boundary values. So that was the main approximation we made. So this is quite poor, actually quite poor approximation, as we will see later. But anyway, for a while, just to take this approximation. Okay. Then now what we can do is, yes, so we can calculate many different components by taking the partial differentiation. So maybe you remember actually what we have to do is like this. For example, so if we consider for example the residue of electron continuity evaluated at I, node I, can be represented as just Jn evaluated at I plus half minus flux or current density evaluated at I minus half. So in order to actually in the Jacobian matrix, what we have to calculate is like this. This residue function is derived with respect to, for example, n sub I plus 1 or other quantities like n I and I minus 1 or phi I plus 1, phi I or phi I minus 1. However, since all of us understand that this Rn can be written as just a linear combination of this Jn, another Jn, so we can relate this quantity and other quantity like Jn I plus half, which is partially derived with respect to these quantities. That's the reason why in here I just to show you some quantities like round Jn over round n. Although what we wanted to calculate is the round n, and here is the residue vector with respect to our solution variables, but it is closely related with partial derivative of our current density shown here or shown here. So I hope that everybody can understand this one quite readily. So now let's go to the more practical discussion. So how can we arrange variables and boundary conditions? So what we have to do is, previously we had just non-linear Poisson equation only. In the case of non-linear Poisson equation, although we have used certain expressions like electron density and hole density, however, that was, or they were, just some functions of electrostatic potentials. So, simply speaking, there was only one single equation and therefore only one solution variable. That was the situation. However, now what happens? Now we have three different equations and we need three different solution variables. That is the situation we have to conquer. So, of course, we have already considered this kind of multi-variable cases when we consider process simulation, but let me just make a concrete way to arrange these variables. So we have to solve three variables: electrostatic potential, electron density, and hole density at each vertex. Each vertex means that if we have several points, for example 4 points, then we need 12 unknown variables. Why 12? This is simply 3 times 4, number of vertices, and this is the number of unknown variables per vertex. Okay, so we have to have certain number. So how can we make the grand system containing all of these potential electron density and hole density and defined at every position? So here we have one possible way. Of course, this is not the only way we can arrange our variables, but let me just make some unification. So, simply speaking, please assign your potential first and electron next and hole last. So, simply speaking, phi and p, phi and p, phi and p. That is the way of arrangement. Then what is the difference between these? Here we can find several phi values. Here we have phi, and here we have another phi. Of course, here we will have another phi. What is the difference between them? This is the phi value defined at the zeroth vertex, and this is the first vertex, and this is the second vertex. So what is the index for this? The first one. This one has 0. This one has 0, 1, 2, 3, 4, 5, 6. So you can easily understand for your electrostatic potential, then you have the index in the grand solution variable multiples of number 3. Just 0, 3, 6, that is given by simply 3 times the index of your vertex. And how about your electron density? Then it is quite easy, because always the electron density comes next to the electrostatic potential. We can just add one more. And in the case of a hole, we can just add another one. So we can just have plus 2. So this is it. So here I just shows the vertex index and 3 times index, 3 times index plus 1, 3 times index plus 2. They are suitable index for our unknown variables. Okay, so are you all with me? Then let me just give you a quick question. Then if you have number 9, what is it? If our one variable has the index like number 9, then you can understand, oh, this is nothing but phi 3. So this is the electrostatic potential defined on the third vertex. Okay, so how about then 13? In this case, that is corresponding to electron density defined on your fourth vertex node. Okay, now everybody can understand this kind of operation quite easily. Of course, I wanted to emphasize that is this the general approach suitable for every case? Actually, not. So one difficulty comes from this specific case. For example, let's think about this case. Let's say here we have a metal, and here we have oxide, and here we have silicon. Although we have 4 different nodes, then how many solution variables are needed? Of course, for this silicon part, we need 3 variables, and here we need 3 variables. And how about this point? This interface point between oxide and semiconductor, we need 3 variables. Then what is your opinion about this oxide metal interface? Do we need three variable? Let's assume that. Then when we say we still need three different solution variables, it means that we must define the electron density, and we must define electron density and hole density and electrostatic potential. However, this point is just the interface between oxide and metal, so actually we don't have to care about electron density and hole density because the oxide is treated as a perfect insulator. So what is the electron density? What is hole density? That is a meaningless question. So simply speaking, in this case, actually what we have to do is just number one, only electrostatic potential is needed to specify this system. So if we adopt this kind of thing, then our solution variable will not be no longer having 12 unknown variables, but it will have a more compact form having only 10 unknown variables. Okay, so are you all with me? If we have only silicon variables or semiconductor materials, then this kind of approach is quite accessible. However, if we have different materials, especially like oxide or nitride, such kind of insulating material is involved, then this number 3 based indexing system will fail. Okay, so however, for while just consider only silicon material only, it means that we don't care about the MOS systems, which is the far most important application of our TCAD device simulator. Okay, but anyway, for a while, we are just at the starting point of implementation. For a while, let's just adopt this kind of convention. Then now we will have this kind of form, like this is a Jacobian matrix, and this is solution variable. Actually not exactly solution variable, but it's a update. So instead of a solution variable, let's say that this is update vector, and here we have residue vector. Okay, so what is the residue vector? So this is the Poisson equation evaluated at zeroth point, and this is a Poisson equation evaluated at zeroth point, and this is a this is electron continuity evaluated at zeroth point, and hole continuity at zeroth point. And the first point we have another triple, uh, also another one. So this is the residue, and here we have Poisson equation. So once again, let me give you a simple question. What is the physical meaning of this a sub 0, 0? Can you write it down? So this is nothing but this is the Poisson equation evaluated at zeroth index, because this 0 is corresponding to this index. And what is this 0? This is corresponding to electrostatic potential at zeroth point. Are you all with me? So then let me just give you any kind of a question like 9, 10. What is it? If you have some compound like 9, 10, this is corresponding to your Poisson equation at third vertex, because number 9 is corresponding to this physical meaning. And how about the variable? The variable is corresponding to Yes, this is now electron density evaluated at number 3, because 3 times 3 plus 1 is corresponding to the number 10. So now you can understand this kind of physical meaning is assigned to this one. So simply speaking, although you have the same law, maybe you can find a big difference between, sorry about that. So once again, our pencil is stuck. So please wait for a while. It will be recovered soon. Okay. So now think about this one. Think about another component of A 9, 9. What is the physical meaning of this quantity? This is the dependence of your Poisson equation evaluated at the third vortex with respect to the electrostatic potential of at the third vortex. So although maybe that will be they will be assigned in this way. So here if you have a matrix, then you have the ninth row, and there will be certain number corresponding to a comma a sub 9 comma 9, and there is another component like a sub 9 comma 10. So although they are just neighboring entries, but their physical meaning are completely different. This is corresponding to the dependence on the potential and dependence on the electron density. So my question is, what is more sensitive to the value 1 change in our conventional what SI unit system? If you change number 1 here, that is corresponding to you changes your electron density like this way, because the unit of your electron density is per cubic meter, and this is corresponding to 10 to the minus 6. Excuse me. Okay, oh, sorry about that. Oh, yeah. Okay, so this is true. So 10 to the minus 6 per cubic centimeter is really extremely small quantity. And how about this change shown in here? What is the unit for this electrostatic potential? This is in a unit of volt. So when you say the A sub 9,9 component, then you are now just observing what happens to your Poisson equation when you change your voltage by 1 volt. Oh, that is really huge difference. And when you see the A sub 9,10, then you observe once again the change of your same equation, Poisson equation at the third node, when you change your electron density by amount of 10 to the minus 6 per cubic centimeter. Then which one will have larger value and which one have lower value? So obviously you can find that this one is much larger magnitude, and this one will be a much smaller magnitude in your matrix. So simply speaking, your Jacobian matrix, when you actually build this matrix, you can find that the entries in your Jacobian matrix can show quite much difference in the entries magnitude. So please note this situation. Okay, then yes, I think that's it for our discussion. Uh, and I have to mention this one boundary condition again here. The second line in this paragraph just shows that carrier densities are fixed at two boundaries. For example, let's say that this is a zeroth node, and here we have a continuity equation and whole continuity equation. However, what was the boundary condition for our Poisson equation? We just said the electrostatic potential is the equilibrium electrostatic potential. Therefore, instead of solving the Poisson equation, we set the boundary condition. Quite similarly, for electron continuity, instead of the electron continuity equation, at the boundary node, we just say that electron density is given as the equilibrium electron density. In the case of whole case, we just said whole density is just given by the equilibrium whole density. Then who decides this equilibrium densities? Like this one and that one. Yes, actually, doping density determines this one. Okay, I think that everybody can understand this one quite easily. For example, let's say that we have the doping density like 10 to the 17 per cubic centimeter. Then what is your equilibrium electron density and equilibrium hole density locally? So it will be 10 to the 17 per cubic centimeter, and it will be about 10 to the 3 per cubic centimeter, because this is n-type dopant, so this is n-type, so electron density just follows the doping density, and hole density just obtained by this relation. In any case is at equilibrium, the product between electron density and hole density should be equal to square of your intrinsic carrier density. So since this number is more or less given by 10 to the 20, so that's the reason why I just estimated the whole density like 10 to the 3 per cubic centimeter. Okay, are you with me? So do you have any question on this uh, arrangement of variables and boundary conditions? Okay, if you have any question, then please interrupt me anytime. Then let's go to the, the next slide. So I assume that fortunately you can implement this problem without any difficulty. So that is my assumption, and this is once again this is your task to reproduce these graphs. So fortunately you have all of you have already solved the nonlinear Poisson equation. So at equilibrium, the nonlinear Poisson equation gives you the exact solution. So now you have the solution at a given system. So what you have to do is starting from your exact solution. However, this solution is just containing electrostatic potential only. So reconstruct electron density and hole density out of your electrostatic potential, and just to make this grand system containing Poisson equation, electron continuity equation, and hole continuity equation. Since your solution is actually the exact solution, when you try to apply the Newton-Raphson method for this expanded system, you will find that it doesn't take much or many iterations to get the solution, because you are quite close to the solution. Actually, you are at the solution. Okay, any question? So I mean that I wanted to give you simply this way. You have, for example, you have solved this equation. For example, what is the answer? Its answer is x equal to 1. This is trivial. However, now you want to solve x minus 1. So starting from the solution of this simple equation, and now you start to solve this more complicated equation which shares the same solution. Then what will happen? Then you will get almost immediately the numerical solution. That is the situation. At equilibrium, you have already the solution. However, what I wanted to ask you is just to reproduce the same solution, not from the Poisson equation, but from this drift diffusion equation containing Poisson equation, electron continuity equation, and Hall continuity equation. So you can do it. Then this is your homework. Once again, you have 1 week. You have 1 week to solve this system. And so since you have already done it in your previous program, so 3 p.n. junctions. So 3 p.n. junctions, which means that you have the given donor density, however your acceptor density were varied in 3 cases, and for that, for those p-n junctions, please use the drift diffusion simulator. Then simulate the same devices. So what will happen? If you just apply your newly developed drift diffusion simulator, then you will find that within a few iterations, you get the solution that seemingly is the same solution quite easily. Okay, so are you all with me? So let me just repeat this one. Let me just make it more concrete. I hope that this was in our yes, this one. This one was done in your homework number 13, and here you have 3 different values of your p-type dopants, acceptor dopants, and you get the electrostatic potential shown here. My question is, in this new homework 14, just to get the same value, just to get the same solution starting from this solution. But the problem itself is no longer the nonlinear Poisson equation, but the drift diffusion equation, which contains a Poisson equation and 2 continuity equations, should be applied to solve this system. Then you will get almost identical solution. Do you have any question on our homework number 14? So if you implement your drift diffusion simulator without any error, that is quite a seldom case, then you will get the solution immediately, almost immediately. However, we are all human beings and we are prone to make mistakes. So sometimes when you make mistakes, although we start from the exact solution, your drift diffusion simulator may not converse easily. Oh, then what you have to do is, oh, I made something wrong in my newly developed drift diffusion simulator. Then please debug your drift diffusion simulator. When you make good implementation, then you will find that you get the solution easily. Okay? So although just saying this one is quite simple, but in actually, uh, that will take some time. So please start now. So start today, and you will get many difficulties. So simply speaking, previously you consider nonlinear multiplication. It was just having only one solution variable, and now you have phi and p. The typical problem or typical issues by students is they sometimes make some confusion in treating their index system. So, for example, if you index this number 10 to 11 or number 10 to 9, then what will happen? Your Jacobian matrix will be just destroyed, dis, uh, distorted, and your A matrix is completely wrong. Then what you will get is your update vector is also completely wrong, because your update vector is simply given by this equation, and when you have a wrong matrix, then although your legit function is correct, but your update will be directed to a wrong direction. Then yes, solution does not converge, it will diverge. So please, from my own experience, the most frequent way to destroy your code is just confusing, confusion on your index system. This is the typical way you mess up your program. Okay. Okay, so this is our homework number 14. So in this Wednesday, we will not have any further homework. So please concentrate on this homework program. Maybe you may understand the effort required for this problem. I will not give you any further additional homework assignment, and 1 week is fully assigned to only this simple problem. Means that you have already the solution, and you can just reiterate the same solution. But I gave you 1 week. It means that to everybody, its real implementation will be quite challenging. So please start today, although you have sufficient time to do that. Okay, then let's go to our bias lamping case. So bias lamping is required for realistic cases. So maybe all of you have already attended some courses for semiconductor device. So actually PN junction is the first device we are uh, studying in that course. PN junction. What is this PN junction? Electrical property of this PN junction. So P part, that is usually called as anode, and when we apply positive anode voltage, then we call it as in forward mode. And when we have negative anode voltage, then we call it as in the reverse mode. So when we have forward operational mode, then this PN junction becomes highly conductive. And if we go to the reverse mode, then this is almost insulating. So no current is flowing. So simply speaking, when we draw IV, current versus voltage characteristics of our PN junction, then we have this kind of, this is the typical graphs we draw in microelectronics course, although we draw it in a schematically way in this way. Yes, here we have a small difference, but in reality, in any kind of reasonable uh, dimension, actually we have no distinction between this horizontal line and our reverse current. Because so compared with this forward mode current shown here, it is way too high. So this is just attached to the horizontal line, and there is a sudden increase of current. Yes, this is the typical behavior of our PN junction. So in order to calculate this kind of operation, what we have to do is quite obvious. Starting from this zero applied voltage case. Unfortunately, this is the only case we can solve up to now. We just always considered the equilibrium solution. So the voltage difference between anode contact and the cathode contact means that the contact attached to the antagonism, that should be zero. So we can always get the solution like this. However, this is not the operational condition of our interest. Actually, we wanted to increase or decrease the voltage. Anyway, we wanted to have non-zero applied voltage. So we must apply that case. Then, how can we do that? So I just make a simple summary on this one. Boundary condition, let's just consider boundary condition. Why we consider the boundary condition? It is because in the case of our continuity equations and Poisson equation, nothing will be changed. So continuity equation or Poisson equation doesn't depend on the boundary values. So nothing has changed. Everything is perfectly the same. The only point we have to change it due to change of the voltage is the boundary condition. And let's consider cathode contact is located at the index 0. And let's say that the anode contact is located at the index n. Then how many vertices are there in this system? Are there n points? No, we have n plus 1 points. So are you with me? Here, for example, let's say that n equal to 100. Then there are 101 points whose indexes are starting from 0, 1, 2, and ending at 100. Then how many points are there? 100 points? No, 101 points. So please don't be confused with this number. Anyway, so if we have this case, then we will have the number 0 and number 300 for what? For the electrostatic potential at two boundary values. For zeroth node, we have number 0, index 0 in our solution variable, and we will have number 300, the index number 300 for 3 times 100. Of course, we will have some numbers like 300 plus 1 and 300 plus 2. What are the physical meanings of these two quantities? This is corresponding to your electron density defined on 100th point, and this is corresponding to your hole density defined at 100th point. But why we don't have any discussion on these quantities? This one just shows 3n. Why we don't care about 3n plus 1, 3n plus 2? Or, for example, why we don't care about R1 and R2? This is the electron density at the cathode contact, and this is hole density at the cathode contact. It is simply because, once again, in this case, we will just apply this condition even at non-equilibrium cases. Carrier densities are fixed at two boundaries. Simply means that the only change when we consider the non-equilibrium case is just change of boundary values of your electrostatic potential. So are you all with me? I mean that let's consider this case. Your anode voltage equal to 0.5 volt and your cathode voltage equal to minus 0.1 volt. If we have to consider this non-equilibrium case, then only two places we must care for is this and that cases. So for R1, we must consider this cathode voltage, and for anode, for R sub 3 times n, we must consider this anode voltage. Okay, so let me just consider this anode contact because this is general. In this slide, I assume that, always assume that cathode is grounded. So that's the reason why cathode part we have no additional values. However, I assume that in the case of anode, we can apply a general value, non-zero value. In this case, our residue function now read like this. Please concentrate on this one. And what is our ultimate goal? We wanted to make this residue function equal to 0. So it simply means that our electrostatic potential at the anode node is simply given by equilibrium potential. That is quite understood. N plus anode voltage. So simply speaking, that is too simple, amazingly simple. Our new boundary condition is nothing but when you apply anode voltage, then your electrostatic potential increased exactly by amount of applied voltage. Then my question is, please write down your more general relation for your cathode contact. You have applied V cathode. Then what will be your residue function R none? Then it should be phi evaluated at x0 minus your equilibrium solution minus the V cathode. That is the new residue function. Of course, in this case, in this slide, as I told you before, I assume that cathode voltage is equal to 0. That's the reason why we don't have any term here. However, in reality, if we have a non-zero cathode voltage, then we must have here cathode. That will be the more general expression for our boundary condition. And of course, this boundary condition should be also considered in our Jacobian matrix. However, it is amazingly simple. So when we consider Jacobian matrix, then this one is just a given number, and this is once again given number. When we take the partial derivative, only this the first term contribute. What is the contribution? The contribution is the potential at the local node. Yes, there is only coefficient 1, and here we have amazingly simple expressions like a diagonal component. So also a sub 0, 0 equal to 1 for this cathode content. So to some of you, it seems to be too simple and elegant to be real. However, believe me, this is the real condition we have to apply to the general cases. But then how can we have such kind of complex behavior over our electronic device when we apply these seemingly too simple boundary conditions? Don't worry, because we have sufficiently complicated equations inside our device. So our device react to this simple excitation, V cathode and V anode, then it will give us this very complicated behavior. Okay. Do you have any question on bias lamping? So if you have any question, then please interrupt me. And since its implementation itself is so simple, because nothing gonna change it except for this boundary condition. Not all boundary condition, only for electrostatic potential part should be changed. That's it. So you can easily calculate the non-equilibrium case. So now I assume that you are eventually succeed to implement this kind of implementation. If you done it, oh, so sorry about that once again. This is not 10 minus 10, that is 0, but 10 to the minus 10, so I made a mistake. This one should be a superscript. And if we say convergence criterion is 10 to the minus 10 volt, 0.1 nanovolt, so we need just 4 or 5 Newton iterations to get the solution at each bias condition. Simply speaking, starting from this 0, then increase or decrease your bias voltage, then you will get 4 iterations to get the solution. Then go in this way. This is the reverse bias condition. And also starting from 0, which can be obtained from your non-linear Poisson equation, please increase your applied voltage this way. Then you will get just 4 Newton iterations to get a sufficiently converged solution. So that is not that difficult to get. Only when you make it correctly. I mean that if you did it correctly at equilibrium, actually this is just to obtain it almost immediately without changing much of your code. But if you implement it in a long way, then every time you try to solve this system, you will get certain numerical problems. So please make a neat code which can be easily debugged by yourself. Okay? So this one shows just convergence criterion, or convergence behavior. So simply you can get the solution quite easily. And however, this number 4 or number 5 or number 2, this is not your interest actually. As a device engineer, what you want to get is this curve. so-called IV characteristics is your interest quantity. You just wanted to draw IV characteristics. Now, although you get the solution, for example, at 0.5 volt, wow, then if I ask you a question, okay, good, then what is the terminal current? Please write it down in ampere unit. Then right now you cannot answer that question. So our next slide is devoted to how can you calculate your terminal current. So terminal current of course can be two-folded. The first one is anode current. At the same time, you can consider cathode current. How can you calculate this anode current and cathode current? So let me just consider just anode current, and you can consider cathode current in a quite a similar way. In order to understand this terminal current, first of all, we have to consider this one. So let's consider anode current, and please try to relate this anode current and electron current density and hole current density. What is the relation between this current density at a given position and anode current? So anode current, do you have any position dependence on this anode current? Anode current at a point here and another point at a different position. We don't have any kind of a position dependence. But in this case, in the case of electron current density, then we must define the electron current density everywhere inside our device. So now you can easily understand the difference between these two cases. This one is position dependent quantity. And how about terminal current, anode current or cathode current? They are position independent quantity. So when you have a certain position independent quantity and when you have a position dependent quantity and you know that they are closely related, then what you can expect is maybe there will be a certain relation of integration. When you integrate these position independent quantities, then we will get eventually position independent quantities. Are you all with me? So then what will be the equation or relation between terminal current and position dependent current densities? So any question? So please feel free to interrupt me. Then let me just consider this one. If we consider this anode current, for example, what we have to do is like this. Anode current is given by just integration of certain quantity called total current density. So although that is written as terms like J, same terms like J and JP, but subscript is different. This one is total current density. That is integrated over certain position. What is the certain position? This is the interface between our semiconductor and anode. So are you with me? So here we have J vector which has the vector dimension, and here we have a dot, and this is so incremental area which has also the vector dimensionality. So we must have the product, scalar product. So this one becomes the scalar product, scalar value, and we just integrate over another content. Of course, instead of this anode, if we just make an integration over cathode, then that will be related with the cathode current. So now say any kind of current, any terminal current can be obtained by this integration evaluated over certain terminal area. Okay? Are you happy?
지금 그러면 에너지 커런트랑 캐서드 커런트를 구분하는
Oh, that is quite a good question. So let me just consider this way. Now say yes. Here we have cathode, and now let's say that here we have anode. Then, although this integration seems to be identical, however, the area of or region for this integration are quite much different. In order to get your anode current, you must integrate it over this surface. And when you consider cathode current, then you must take the integration over this case. That's the reason why we must distinguish these two quantities. Okay, that was a really good question. Yes. So let's say that we have another. Let's say the another one, like let's name it as a gist, for example. If we have these three terminals, then what is current for this third contact? That will be just integration of, once again, total current density, but the integration range should be confined on this position. Okay, are you all with me? That is the difference between this one. But that was a really good question. So I had never thought about the question. So we must care for the range of integration. But the main reason I ask you this question, your happiness about this expression was, the reason was this expression is not perfect. I mean that in some sense this expression is wrong. I mean that. Let me just ask you once again. Now let's say that I terminal current density, a terminal current at a certain terminal is given by the integration of this quantity over its terminal surface. That was my previous assumption. However, I just told you that this expression is not complete and we need further effort to calculate terminal current. The final correction is here we have negative sign. This negative sign seems to be quite annoying and redundant, but that is really important. So everybody in this electronic device adopt this convention, so negative sign. So please adopt this one. Simply speaking, it's like this. If you have incoming current, if your current density flows in this way, then you have a positive terminal current. If you have outgoing, escaping terminal current density, then that is regarded as negative one. For example, let's consider a typical case like this. You have applied positive bias to your anode voltage and cathode is grounded. Then please draw the movement of your particles, charged particles. Your positively charged particles will flow in this way. Yes, because this is grounded and sorry about that. And you have applied a positive voltage. So your particles should flow in this way to arrive lowly biased contact. Then my question is, what is anode current? Is this positive or negative? And my question is, once again, I cathode. Is this positive or negative? The answer is, we always take the incoming current as positive, so we will say that this one is positive. And in the case of a cathode, obviously current is escaping through the cathode, then we will have negative value. Then for this simple, really simple two-terminal device, then we have an immediate result like this. Sum of I cathode and sum of I cathode and I anode should vanish. So simply speaking, I cathode is immediately obtained, can be obtained from I anode. So in some sense, his previous question seems to be quite reasonable. Why we don't have to explicitly calculate cathode current? Once we calculate anode current, then the cathode current can be immediately calculated. However, this is the only case when we have two terminals. Now let's say that we have three terminals. Then what will happen? We will have I1, I2, and I3, and their sum should be 0. Then we must consider I1 separately, I2 separately. Only when we have I1 and I2, then from this current conservation, we can estimate I3. Or better way is, even in this case, we must calculate I3 individually and check whether the current conservation is really holding or not. Check this equality. If we have severe disobey this equality, then it strongly suggests that something is wrong in our implementation. This current conservation should be valid at every case. Really every case you consider, you must have the current conservation. If you don't have this condition, then something is wrong. So simply, I wanted to strongly suggest to you that please don't rely on this current conservation. Current conservation should be your result. Current conservation should not be your leverage or your knob to evaluate something, because we are considering more fundamental level. So anyway, let me just come back. Up to now, we have thought about how can we calculate the terminal current at a given terminal. When we have a given terminal, then we must calculate the surface integral of our current density. total current density. After that, take the negative sign. That was my lesson. Then the next natural question is, then what is this total current density? We never define this quantity. Then at steady state, this simulation, we can say that this total current density can be regarded as a sum of Jn and Jp. So simply speaking, let me just write down in this way. Then when you wanted to calculate a certain terminal current, then what you have to do is quite simple. Just to make an integration over terminal surface of your electron current density and hole current density. That's it. So let me just summarize. I just spent quite a long time about explaining this simple rule, but my final answer for evaluating the terminal current is summarized here. If you wanted to evaluate the terminal current, please make surface integration of your total current density over terminal area. Don't miss your negative sign. This is convention, worldwide convention, universal convention we adopt in this field. Okay. So in the case of 1D case, this integration becomes quite easy because we have just one-dimensional case. Then here we have a surface area. What is the surface area? This is nothing but just area normal to our one-dimensional direction. If this is the direction of our one-dimensional x-axis, then we will have just a plane normal to x. Simply speaking, YG plane. So area inside this YG plane is the multiplication factor for this integral. So simply speaking, let me just make a 1D expression. So I terminal, I onward, and here we have Jn, Jp and Jn, and Jp and Jn, and here we have a negative sign, and what's gone? For this integration, it becomes just area of your device. Who decide the area of your device? You decide the area of your device. When you perform your 1D simulation, you say that, okay, my device has 1 micro by 1 micrometer cross section. Or you say, my device has 1 centimeter by 1 centimeter. Or you say 1 meter by 1 meter. This is your choice. When you change your cross-section area of your cross-section, your A value, area value will be increased. So your terminal current itself will be increased. However, that doesn't change the terminal current per unit area, because your terminal current is simply multiplied by your area. So sometimes in your 1D calculation, instead of this the real current itself, then more frequently we wanted to calculate the terminal current normalized by your area, surface area, device area. Okay, are you with me? Okay, so since time is up, although we have more result in our lecture material, I will just stop here and we'll continue the discussion on this Wednesday. Once again, as I told you at the beginning of our lecture class, so on this Wednesday, we will have a usual on-site lecture. However, the next Monday, we will have just a recorded video for commenting on your term project proposals. Okay, so please don't come to this lecture room on next Monday. Okay, thank you for your attention and bye.